I'm J.S. Cournoyer. I'm one of the co-founders and partner at Real Ventures. It's a venture capital firm based out of Montreal that invests in mission-driven entrepreneurs who want to make the world a better place using technology. And I have here Christian Weedbrook, who is the co-founder and CEO of Xanadu, a quantum computing company that we invested in 2 years ago, or was it last year? Yeah, 2 years ago. We're here to talk to you about quantum computing and the impacts potentially that it can have on society, but also what it means for fund managers like yourselves. So Christian, well, thank you for being here.
No problem. Thank you for inviting me.
It'd be great if you could maybe start by telling a little bit about yourself and how you got into quantum computing.
Yeah, for sure. So thank you everyone for being here. So quantum computing is a very fascinating topic. It's kind of a science fiction sort of topic in some sense. So I started in this field through doing a PhD in quantum computing. That was in Australia, and before that, I was looking at doing mathematics and physics. And around this time, quantum teleportation, quantum computing started becoming more and more popular. So I thought that'd be a great thing to get into. It's very fascinating. It has a lot of practical applications, and also uses quantum physics at its heart, which is a really unusual sort of theory that describes the atomic world. So I did a PhD in this photonic quantum computing, which is what Xanadu looks at, so using light to process and manipulate small bits of light, photons, and learned a lot of things during that period. And then after that was a postdoc at MIT, and it was an amazing time because I got to work with Professor Seth Lloyd. Seth is now actually our chief scientific advisor at Xanadu. And he was one of the people in the early 90s who kind of started the field of quantum computing. In fact, in 1982, Richard Feynman, who's credited with starting quantum computing through a speech that he gave, suggested that, in one way to sort of phrase it, the best way to understand a quantum system is to have another controllable quantum system that can simulate the physical system. And Seth actually showed how to do that mathematically, that indeed it was possible. So I learned a lot from him and continually worked with other researchers in the field. After that, went to the University of Toronto, continued in the field of quantum computing using light, and then started Xanadu in September 2016. And the idea was to use the community that I was involved in, this photonic-based approach, and to form a company around that. And after we got our seed funding, which, as you mentioned, Real was an important part of that, we built a company around that, and we will be raising our Series A, announcing that. It's actually closed now, and we have about 35, 40 people. And it's an exciting time with many interesting applications in finance.
Great. So, what is quantum computing, and how different is it from the existing computing landscape that we're used to?
Yeah, it's fundamentally different. It's kind of like night and day, really, with what we're used to. One place, I tried to make it as simple to understand, particularly for myself, because it's such a crazy thing. But these laws of physics have been backed up now through experiments in the last couple of decades. So one way I look at it is from a practical point of view. It's still a computer, but it does some really amazing things in terms of speed and accuracy for potential customers. And the reason it can do these things, and also the things that it can do is really intractable problems. It can make them tractable. So things that would take even AWS or Azure thousands of years to find the solution to, find complex portfolio optimization, drug discovery, and so forth, in such a short amount of time. Days or weeks at most, depending on the problem size. So it's a new type of computer. It does really incredible things, much faster. And it's based on, the reason it can do this, it's based on different laws of physics. So ever since we were all born, we play with tennis balls or soccer balls, and we'd kick them, throw them, and we're not surprised about how they evolve in time. But the quantum realm is very different. And there's characteristics such as superposition and entanglement These properties are inherent to quantum physics. And the idea there is let's use these different properties to do computing. And once you can do these sort of extract these features of entanglement, then you see these remarkable speed ups. So to an end customer, you won't know really what's going on under the hood. It'll just be, I have a tough problem. I can do it, so much faster. I can now look at problems that were, extremely hard to do, and now I can do them. But the underlying layer of it is quantum. And the simple way to understand quantum, you hear this a lot in media, is the ability to do two things at once. So a traditional computer, getting back to your question about how similar it is, traditional computer has an input, it has the gates, logic gates, and it has the output. Now quantum also has that, so there is that similarity there. So you have quantum inputs, quantum gates, and quantum output. So with a traditional computer, if we simplify it extremely and say, let's just say zeros and ones, a stream of zeros and ones are going to these logic gates. A quantum computer can do that, but you actually have 0 and 1 existing at the same time. That's the common way to understand that. So the reason why that's great is for 1 bit of classical information, you now have 2 bits of quantum bits. Mm-hmm. And the same 1 gate that acts on 1 bit can now act on 2 bits. So you think, well, that's pretty cool. Maybe that's the same as having 2 processors, and that's true. But these things scale exponentially. So if you have 300 qubits, so kind of like 300 bits, but in the quantum regime, you now have every single processor in the world. If they acted in parallel to sort of mimic this, it couldn't do it.
Right.
So the scaling is phenomenal.
So with a tiny computer, really, you could have the processing power of the entire planet. Yeah,
exactly. So the idea is that 2 to the 300, which is the amount of states that a 300 qubit quantum computer has.
Yeah.
There's not even that amount of atoms in the universe.
Sure.
So it's ridiculous.
So we have a lot of money managers, large portfolio managers in the room. How can quantum computing help them?
Well, one way I look at that is this is a new advancement in computing. And if we take this whole room, we would say that wherever we are here on stage is what traditional computers are capable of doing. But a quantum computer can now fill out this whole here. So the amount of computations it can do far exceeds that. Now you sort of add that to the fact that in the 70s and 80s, computing power is really what made the differentiator for financial institutions. I mean, look at where we are today. If we didn't have computers, it'd be a crazy, crazy thought. So now quantum is a supercharging of that. So it really is a case where financial institutions should be seeing this as the next evolution, step function, however you look at it, revolution of computing power, just happens to be quantum. And really a financial system can be thought of as a complex system. So as you add more and more elements to it, it becomes intractable. So at Xanadu, we're looking at things like Monte Carlo simulations.
Yep.
So these are things that are used for options and derivative pricings. We've talked to a lot of banks and work with banks on this. And these options and derivative pricings typically take overnight. So that's great, because we don't want to solve a problem that you can do very fast anyways. Mm-hmm. So for a certain book size, it takes an overnight run. A quantum computer can actually do this in a couple of minutes. Wow. So that's a first-hand account of what's happening there. Another one is portfolio optimizations. Again, a complex system. If you add more and more objects to this portfolio, then it just becomes intractable. So either people don't want to wait weeks or months to simulate these things. A quantum computer allows you to do these things in principle in real time. So it will transform the industry in ways that we can't really see yet.
So could it also, so in the same way that it helps speed up what firms do today, could it also help add complexity to some of these existing problems? So for example, in context of a portfolio optimization, add more parameters, complexify the problem, but use quantum to solve it.
Yeah, exactly. So one way to perhaps think of that is we have 2 parameters we can play around with. How fast you can do it and the accuracy. So getting back to your point, you can kind of say, well, look, it normally takes us X amount of hours or X amount of minutes. We're okay with that. But now we want to keep the time fixed, but increase the accuracy, which is equivalent in some sense to throwing more and more things at it.
Sure.
So you can trade off the accuracy and speed at the same time.
So in a way, you could improve returns without increasing your risk.
Yeah, exactly right.
Great.
Exactly.
So now, are we talking about technology that is in the lab and that will be available like in 2050, or is this something that's closer? Like, what's the timeline to have some of that tech being implemented in the real world?
Yeah, so the first point I'd make is it depends what sort of quantum computer you're talking about, without being too cagey about it. And the reason I bring it up that way is that quantum computers already exist around the world. We have some in our lab as well in Toronto at Xanadu. But no quantum computer at the moment can actually beat a traditional computer.
Okay.
So now it's about the promise of what quantum computers can do. So what we have now is we have simulators. You can actually simulate the effect of as if you had a quantum computer up to a certain point.
Right.
If you could do it past that point, you wouldn't need a quantum computer. But one of these, quantum computing is one of these things that suddenly it's not there and the next day it is. So we're roughly, tens of qubits at the moment, both us and other companies around the world. So we're looking at a quantum computer in the next 1.5 to 2 years, where you can actually see, for certain problems in finance, actual improvements to what you can do with classical computers today. You can kind of look at the spectrum of how things will evolve over in quantum computing. Intel had first chips in the 70s, and they're still bringing out chips.
Yes.
So it'll be like that. Each chip that we bring out will be more and more powerful, and it'll iterate over the coming decades. But in terms of when it will be valuable, we anticipate in the next 1.5 to 2 years. That's when a quantum computer can actually solve something of interest. Specifically, it'd be a special purpose quantum computer, the same as we have GPUs or some kind of AI processors. And portfolio optimization is one of the key aspects as well. And actually, sorry, I should mention that because this is kind of a switch, suddenly it's there, it's not there yesterday and it is there tomorrow. It's one of these things where it's not like just releasing a latest Intel chip. You have to work very closely with customers, in this case financial institutions, to develop these quantum computers. You can't just release a quantum computing chip and then expect customers to know how to use it. Because this goes back to the differences between quantum computers and traditional computers. You need to work closely to understand how to adapt customers' problems with our quantum architecture. That's fundamental and key.
Right.
So we've been actually working with banks and doing POCs, and they say, look, this is the type of problem. These are the type of options and derivatives. These are the sort of portfolios we have, and we have to tailor our mathematics to their mathematics. So that's a good time now to start getting involved, and that's why we're doing POCs, because when that quantum switch gets flicked on,
right,
this would be a huge competitive advantage.
So that was my next question. So do you think that the investors that will use quantum computing, even the initial versions that are going to come out over the next 18 months or so, do you think they will win? They will become the leaders in their market as a result of using quantum computer? Will that be the difference?
It could be. It could be a difference in a particular vertical.
Right.
If you kind of look at AI now, so AI is kind of where quantum is, but maybe 5 years before that. And the AI technology already exists. It'll get better. More computational power will get thrown at it. But for all intents and purposes, AI technology exists. But now it's up to entrepreneurs to decide where are we going to dominate. And so every vertical is affected. So no one company can actually say we're going to dominate finance, logistics, drug discovery using traditional AI. And I think quantum will follow a very similar trajectory. So in terms of your point, whoever focuses on finance will have a good leg up there. But other quantum companies may say, look, we're going to look at drug discovery and pharma and sort of dominate there.
Right.
So it depends where your interest as an entrepreneur lays.
Okay. What impact will or could quantum computing have on the development of AI?
Yeah, that's one of the big use cases for us is the quantum version of artificial intelligence and machine learning. We're one of the leaders of that area. And essentially, you can kind of think about these two areas I mentioned, speed ups and also precision. Well, they apply in machine learning. So you can either train so much faster, orders of magnitude, or the precision of this can actually be improved. So you have the training and also the prediction. Both of these can be sped up. There's also a lot of models in AI that the models are getting more and more advanced, and you need different methods to actually compute certain functions and just get an output. Yeah. And we're seeing that being motivated, and I think Real's invested in sort of AI special purpose hardware. Nothing to do with quantum, but just sort of AI purpose. And there you can see it's a good example. Look, the traditional hardware needs to be adapted, whether it's GPUs or ASICs, to this particular problem. So quantum can be thought of as the next thing on the pipeline coming through of that.
So a big concern right now in the financial sector is around cybersecurity. A lot of investment is being made there. Some folks are worried about how quantum can have an impact on that. What are your thoughts? Is it something we should be scared of? How can we prepare? Is there a world in which quantum computing thrives and systems, IT systems, are still secure?
Yeah, one of the just sort of background, I guess, for people who are not sure about this, one of the first early use cases of quantum computing, it was mathematically shown, I think in '94, that if a quantum computer existed of a certain size, it could actually hack the internet security. Specifically, it's RSA and elliptic curve, the type of cryptography behind it. One point to note about that is that type of quantum computer, I mentioned we will follow a sort of timeline like Intel. Every year we're getting better and better chips. Most people in the industry, I would say, that type of quantum computer that can hack the internet is still 10 plus years away, unless there's a huge breakthrough. But it's definitely not the near term, the next couple of years. So that's good because there's now companies out there, software companies that are looking at changing RSA and elliptic curve to more robust quantum safe algorithms, essentially. So the idea there is RSA and elliptic curve. It's a hard mathematical problem, and that's why it was thought to be secure. When it was developed in the 70s, it's quite fascinating. They thought it would take millions and millions of years for a computer to hack this.
Yeah.
But then as we saw more powerful processors, and then we saw the network capabilities of computers, then people actually hacked it. So you increase the size of the key, and it becomes stronger. But at the core of this, the reason why it's tough is it's a hard mathematical problem, and a quantum computer is very good at it. So people now, there's companies being formed of choosing different types of mathematical problems that a quantum computer looks at and thinks, well, I can't do anything there.
Okay.
And a quantum computer won't solve all the world's problems. It'll solve a subset, but very important problems. And so the switch to quantum safe encryption is underway, and that's enough of a time frame to make sure financial institutions and others are safe.
Great. So we know technology is neutral. It doesn't hurt. It doesn't make the world better. It doesn't make the world worse. It's the humans that build it, that give it the flavor. Like we've had the digital revolution, and that did help improve the material world in many ways. But it's not clear whether it's also helped on the emotional well-being of humanity, and we see things like Facebook and Google having very negative impacts. How do we make sure that as quantum gets going, which is another revolution that is hard, it's hard today to predict the impact that quantum will have on society. I don't think anyone could have predicted at the beginning of the digital revolution that we would be living in this world today. How can we make sure we maximize the potential positive outcomes that it will have on society and minimize the potential negative outcomes?
Yeah, that's a really good question. I think it's good that quantum is coming where it is now.
Yeah.
So it's not the first in line. It's sort of trailing now AI. And there's better than me. There's things like AI ethics and companies and committees being formed based on looking at what are the long-term consequences of things like that. So quantum can kind of stand on the shoulder of these types of movements, and Facebook is another one as well. And people, just in general, are we spending too much time on social media and things like that? So there's a lot of things that we'll learn from these two phases that we can actually adapt to quantum. More so, though, I think an openness or transparency would be an important policy. So for instance, what we do at Xanadu is any good ideas, we'll patent them for sure, but then we release all the papers to the archive or open source papers. So that allows other researchers to understand what we're doing and build a community around that of openness. We also our software stack, so we're full stack at Xanadu. We build the hardware and we also have the software layer on top. That's all open source as well. Again, coming back to this idea of transparency. So I think those being as open as possible and sharing this and letting the community know will go a long way. And also building upon anything we've learned through AI, ethics and policies will be key. The other ways is how do we get our infrastructure and our quantum computers to people everywhere? And we do that through, we'll be announcing a cloud platform for Xanadu, similar to be fair, other companies like IBM have one also. But I think having more openness in terms of having it available to as many people as possible. Now, like you said, it can be used in whatever way.
Yeah.
But I think you can't halt technology fundamentally, but as being as transparent as possible, putting in place even standardizations, policy of standardizations will also help.
Great. Well, we're out of time. Perfect timing. Yes. And so we're going to keep enough time for the crowd. If you have any questions, please raise your hand. I think someone can come with a mic for Christian. Any questions? One question. All right. Thank you.
Just a simple question. You identified a big gap between the current and the potential, and I don't know if it's possible to say in layman's terms what needs to be achieved to get to potential and how long you think that might be.
Yeah, in terms of time, there'll always be this trajectory where we're always getting better and better. So one of the big milestones that's needed is some form of error correction and fault tolerance. So if the quantum world interacts with our world, what happens is the quantum world and all its really interesting properties that we can leverage, it dissipates those properties. It becomes more like our world where we don't see entanglement and superposition. So what that means is we really want to isolate the quantum world from our own world, so therefore a quantum computer from our own world, which is kind of ironic given the fact we want to use it in our own world. The way you do that is through error correction and fault tolerance. Essentially, you make the device more robust against errors. Our world seeps into this quantum world and creates errors. So, and then the more errors, you can think of that as just losing its power to provide these speed-ups. And this whole thing is known as decoherence, or a lack of quantumness. Becomes more classical. So that's really, it's a tough problem. We're in this next 2 to 5 year time frame where it's known as, well, what can we do with a large amount of qubits, but they are noisy. They still have quantum effects, and let's see if we can utilize them to do some interesting things. So they're really the key problems. For us, it's kind of interesting for photonics. If you shine lasers through any medium, fiber optics, telecommunication networks, it picks up noise. There's a certain amount of loss. And so our chips are the size of a thumbnail, and there's still loss even on a very small chip. And loss essentially couples in noise into our system, and again, it has the same thing. It becomes more and more like a traditional computer and loses its speed ups. So error correction, again, plays a role there.
Other questions? So I have one. So you mentioned two terms, superposition and entanglement. Mm-hmm. For the benefit of the crowd, maybe it'd be interesting to give just a little bit of
sure.
clarity on what that is.
Yeah, so superposition is, I would say, is originally a mathematical term. So it just means if you've got two entities, A and B, you're simply just summing them up. So you've got A plus B. It's quite simple. What that means physically is you can actually have physical systems exhibiting this superposition or this addition of things. Yeah. So a good example, say with light, a photon is a little bit of a chunk of a laser. Photons can have certain properties. One property is it could be, as it's going through space, it can be angled this way or polarized this way or any way you want it. And so typically something would only be one of these possibilities. So this could be a 0 and this could be a 1. And you can actually have a superposition, both happening at the same time is the common sort of way to phrase it. And you can create systems where it's like the light switches on and off at the same time.
Right.
You hear the famous example of the cat's dead and alive. And you have systems at the quantum level that can do that. So that's superposition. Entanglement essentially means you can have correlations between two systems, again, let's say A and B, that you cannot have classically. And so there's a famous example that Einstein and others came up with. If you have two particles, A and B, and you do something to them, you interact them, and then you take them one to the other end of the universe and the other one to the other side of the universe. If you do something to this guy here, this other B here will be affected in some way. And you can actually use this property of entanglement for things like computing, security, and other things. And essentially, you cannot do that through any classical methods or means. And that's really the source of the speed up.
Great. Thank you. Any other questions? Yes?
Hi. I realized that you said you were at MIT, but your company is based in Canada, right?
Yes, that's right.
Can you explain a bit, like, why did you choose Canada to found your company, and how is your talent there distributed?
So I chose, so originally I was in Boston, and I love Boston, it's an amazing city, and then I got a job offer in Toronto. As soon as I arrived in Toronto, I just felt like home. I'm not sure exactly what it was. It's just an amazing place. I come from Australia originally, and it's quite a different place, but there's a lot of similarities as well. I love the big city feel. You know, since I've been there, the entrepreneurial side has taken off, as it has in Montreal and other places as well. So it suited me personally, and also the idea that now raising money is possible in Canada. And talent-wise, you have Waterloo, University of Toronto you can draw upon. Toronto is also great strategically as well. You know, we're an hour flight away from Boston, so we can tap into that market, so the East Coast market essentially. So they're pretty much the reasons. The cold I actually like. Coming from Australia, it's kind of flat. You don't really see the 4 seasons, so that was another personal reason why I love Toronto.
Other questions? No? All right. I guess we're done.
Great. Thanks, James.
Thank you very much.
Thank you.